Run Docker images, and you get a number. 2 gigabytes, say? That number is technically real and functionally a lie. Not because Docker is trying to deceive you, but because that single number is hiding a file system architecture, a caching system, and at least 2 documented, real bugs filed against Docker's own issue tracker that have quietly bloated production images for years. We are going to autopsy both of them, and by the end you will know exactly where your wasted gigabytes are hiding and how to stop feeding them. Start with what a layer actually is. Docker's own documentation is specific about this. Each layer is a set of file system changes, and once created, that layer is immutable. It never changes again. When a container runs, Docker extracts those layers and stacks them using a union file system, then sets the container's root to that unified view. So an image is not a single file system. It is a stack of frozen diffs, and the OCI image spec is explicit that they apply in strict order. Base layer at index 0, everything else stacked on top, each layer's change set applied on top of the last. Here is the detail that breaks people's mental model. When a later layer deletes a file, say a run or m-rf in a cleanup step, the OCI spec says that deletion is recorded as a whiteout file, a special marker layered on top to hide the file from view. The file is not gone. It is still sitting in the earlier, immutable layer underneath, taking up real disk space, just invisible from the top. This is the first reason your image is bigger than it looks. Cleanup steps that run after the mess was made do not erase the mess. They just paper over it. Now the first autopsy. In a real issue filed against Docker's Moby repository, issue 5505, a developer added about 5.5 megabytes of new application code to an image that already had roughly 200 megabytes sitting in a directory from an earlier bundle install step. Their next instruction was a chown on that same directory, just adjusting file ownership. Here is what the layer sizes came out to. The add layer, 204.1 megabytes. The chown layer that followed, another 204.1 megabytes. The original bundle install layer, 203.2 megabytes. From 5.5 megabytes of genuinely new content, the build produced over 600 megabytes of layers, because changing permissions on an existing directory forces a full copy of that entire directory into the new layer. This is exactly why copy-chown exists now, and why touching ownership after the fact is a quiet tax almost nobody notices until they run the numbers. Second autopsy. Docker's Overlay 2 storage driver documentation states support for up to 128 layers. A developer filed issue 26380 after their build failed at layer 122, with a max depth exceeded error, well under the documented limit. The real cause was not a layer count at all. It was a Linux kernel constraint. The overlay mount option string that lists every lower directory is capped by a kernel page size budget of around 4 kilobytes, and every layer eats roughly 30 characters of that budget, on top of about 180 characters of fixed overhead. Do the arithmetic, and 128 layers was never a hard architectural promise. It was just the point where somebody's build ran out of string before it ran out of layers. The number in the docs was an approximation of a completely different, lower-level constraint, a string length limit on a mount syscall. So how do you actually see this instead of guessing? 2 commands, straight from Docker's own CLI reference. Docker history shows you the size Docker attributes to every single instruction in the image, layer by layer, which is how both bugs above would have been visible immediately if anyone had checked. And Docker system df, with the verbose flag, breaks each image down into shared size, space this image shares with other images on your host, and unique size, space that belongs to this image alone. That 2 gigabytes you saw in Docker images is the sum of both. Some of it might already be on disk from another image entirely, because layers are content addressed and shared across every image built on the same base. The only way to know your actual marginal cost on disk is to read the unique column, not the headline total. Once you can see the layers, the fixes follow the same first principles. Docker's docs on build cache invalidation are specific. For copy and add, the cache key is a checksum of file metadata, and the modification timestamp is explicitly excluded, so touching a file's timestamp alone will not bust your cache, but a real content change will. For run instructions, the cache key is the literal command string, so a stale run apt get update will happily replay from cache even if upstream packages have moved on, because the text of the command never changed. And once any layer's cache is invalidated, every layer after it rebuilds from scratch. No exceptions. That is the entire argument for ordering your Docker file from least changing to most changing. One early copy of a file that changes on every commit nukes every layer below it, every single build. And the payoff for discipline is not subtle. Multi-stage builds, which let you compile in one stage and copy only the finished artifact into a clean final stage, shipped in Docker Engine 17.05, back in May 2017. Google's distroless project takes it further. Their smallest image comes in around 2 megabytes. That is about half the size of a minimal Alpine image, and under 2% of a full Debian image at 124. And at real infrastructure scale, Uber's engineering blog described their legacy pipeline producing images over 10 gigabytes that took up to 2 hours to build. Their replacement build system, Makisu, cut image sizes by up to 50% and build times by up to 90% on some repositories, largely by stripping build-only dependencies that a naive Docker file leaves sitting in an immutable layer forever. Every gigabyte in that 2 gigabyte number came from somewhere specific. A deletion that was never really a deletion. A chown that copied a directory nobody meant to copy. A cache key that only understood file contents and command strings, not intent. None of it is random. It is all just layers, stacked in the order you wrote them, faithfully remembering every mistake you told them to make. Read Docker history like it is a crime scene, because it is one. If this changed how you write Docker files, subscribe. Compile opens one system like this every single day.